we're going to use the remainder theorem and the factor theorem to help us determine zeros of polynomials and to determine what the factors of the polynomials are. So to get started, before I even tell you what the remainder theorem and the factor theorem are, we're going to answer this question. If we have this polynomial, is x plus 3 a factor? In other words, does x plus 3 go into that polynomial evenly? So to do that, we could do long division or synthetic division, but since we've done synthetic division, let's do that. We have x plus 3 here, so that means we have a negative 3 right here. Our coefficients of our polynomial are 1, 8, 13, and negative 6. I bring down the first number and multiply these together, write it down, and add. Continue. And one more time. And we know we have a remainder of 0. So the answer to is x plus 3 a factor, we now know is yes. In fact, we could specifically write f of x equals x plus 3, right? X minus negative 3, or this x plus 3, times 1x squared plus 5x minus 2. And I want to point out one more thing. If you were to evaluate f of negative 3, you could substitute it into the original function as it was written, or we could substitute it in right here. If we do that, we have negative 3 plus 3 times negative 3 squared plus 5 times negative 3 minus 2. And that equals 0 times, and now I don't really care what that value is. So we see that f of negative 3 equals 0. We're going to come back to that in a minute. Let's do another problem. We have f of x equals x cubed minus 11x plus 5. Same kind of question, is x minus 1 a factor? So let's try. So we'll put 1 here. Our coefficients of our polynomial are 1. Remember, there's a missing term, so we'll put in a 0, negative 11, and 5. So I bring down the first number, multiply, and add, and continue. And this time I have a remainder that is not 0. So the answer to the question, is x minus 1 a factor, is no. The remainder must be 0 in order for it to be a factor. But we do know that f of x is equal to x minus 1 times x squared plus x minus 10 with the remainder added in. So if we were going to now find f of 1, I could substitute it in here. I could do it here. 1's not too challenging. Could do it with direct substitution on the original problem, but I want to make a point here. I want you to see this. If we substitute 1 in right here, we have 0 times this quantity, and then subtract 5, so we get negative 5. And let me point this out. This is the point that I wanted to make, besides whether this is a particular factor of this polynomial. Over here, when we did the synthetic division, we found the remainder when we divided by x plus 3 was 0, and f of negative 3 was equal to 0. Those two numbers were a match. Over here, same thing. When we were determining whether x minus 1 was a factor, by dividing by x minus 1, we ended up with a remainder of negative 5. And when we evaluated f of 1, we also got negative 5. These two were a match. That suggests what's called the remainder theorem. And the remainder theorem says this. If a polynomial is divided by x minus c, then the remainder is p of c. The remainder and the value of p of c will be the same. And coming right along with that, as a result of the remainder theorem, we have what's called the factor theorem that says if you have a number that is a zero of a polynomial, or if c is a zero of a polynomial, if and only if x minus c is a factor of that polynomial. So a number being a zero and x minus that number being a factor always go together. So that brings me to the last two examples I want to give you. We'll do this problem right here, and we're going to use the remainder theorem. It says to find p of 3, and of course we could do direct substitution, but I want to use the remainder theorem that says we're going to do the division. I have 2, -10, 3, and -5. We're going to use synthetic division each time. Bring down our first number and multiply and add and continue. So our remainder when we divide would be -32. So our conclusion is that p of 3 would equal -32. We could confirm that that's correct. Let's just do that for this problem. P of 3 equals 2 times 3 cubed minus 10 times 3 squared plus 3 times 3 minus 5. And if we do the arithmetic, we have 54 minus 90 plus 9 minus 5. And that does, in fact, equal -32. But let me make some conclusions here. As a result of this, we know, because of this division, we know a few things. One is x minus 3 is not a factor of p of x. We know that 3 is not a zero of p. And we know 3 is not an x-intercept of the graph of p. Because those three things go together. Let's do one more. So here we are. We're going to find p of -2 using the remainder theorem. So we're going to divide. We're going to put -2 here. Remember, that means we're really dividing by x plus 2. So we have 1, 3, -5, -14. Bring down that first number, multiply and add, multiply and add. I'm going to multiply and add. And this time we do have a remainder of 0. And we can conclude that p of -2 equals 0. So here are our conclusions. That x plus 2 is a factor of p of x. -2 is a zero of p. And -2 is an x-intercept of the graph of p.